Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we irradiate weird and wonderful science through your brain. I'm Ian Woolf. On this radiation shielding edition, Susanna Guatelli talks about protecting astronauts from radiation on their return to the Moon and trip to Mars. Susanna Guatelli is an associate professor in the School of Physics at the University of Wollongong and a researcher at the Centre for Medical Radiation Physics at the University of Wollongong. Susanna is an expert in the use of physics simulation tools that allow the calculation of situations that are difficult to reproduce on Earth, such as the effects of radiation on the human body while on the Moon and Mars. I spoke with her by Zoom, and I began by asking, when we hear about people going to the Moon or people going to Mars, radiation hazards are not the first thing that come to mind.
Yes, the space radiation environment outside the magnetic fields, let's say, of the Earth, the magnetic field is a shield that protects us from these harsh radiation environments. Well, out there, the astronauts are exposed to these radiation levels that can be harmful for their health. Keep in mind that outside the protective shields of our magnetic field, an astronaut will be exposed roughly to about 10 chest X-rays per day.
That's quite a few.
Yes, it's quite a few. So we need to take care of our astronauts, isn't it?
So what is the safe level? Because when you go for X-rays, they do want to know the last time you had them. But what's a normal sort of considered a safe level for that sort of exposure?
So far, the NASA considered a radiation limit that corresponds to a 3% excess risk of death from cancer deriving from the radiation exposure, while the European Space Agency adopts a 5%. Now, for the physicists attending these events, if we want to go in more operational terms, we measure the dose in the so-called dose equivalent that is measured in sieverts, and the limits for NASA depend on the gender and age of the astronauts, but let's say that are less than 1,000 millisievert, so less than 1 sievert on the carrier, during the career, okay? And it's similar for the European Space Agency, but for the European Space Agency so far, there are no different limits between gender, okay, dictated by gender or age.
So for someone on Earth,
yes, 10
X-rays a year is a lot of exposure, let alone in one day.
Yes.
So how does that translate?
Okay, so for a person like me and you, that we don't work in a nuclear facility, or let's say that our annual limit corresponds more or less to 10 chest X-rays, and this is for 1 year. So which are the effects of radiation in astronauts? Because they are exposed to these large amounts of radiation. Well, we have two. One is especially outside. So let's not focus now on the International Space Station, but let's look at to emission to the Moon and Mars, okay, in outer space. So we have a chronic effects due to galactic cosmic rays. This is a background of radiation that permeates the universe. They are mainly protons. Then we have the nuclei of helium atoms and heavier nuclei of atoms. They can produce chronic effects like cancer. So this is a long-term effect due to exposure to radiation. And then there are solar particle events that come from sudden outbursts of radiation from the sun. And these solar particle events can produce acute effects like nausea, vomits, and the radiation sickness, let's say, and worst case scenario, death in a very extreme and violent outburst of radiation from the sun.
So that's a lot of things going on. So there's sudden unexpected solar flares. There's
Yes.
sometimes expected solar flares if they see them coming. And then there's the cosmic radiation from all the other things. So that's a lot of different things. I guess we're protected on Earth by our magnetic field.
Correct. On Earth, we are safe, let's say, because we have our magnetic field that diverts these high energy charged particles. But in the moment that we send astronauts to the moon and Mars, well, there is no protective magnetic field, not on the moon and not on Mars. So this is a problem. And the radiation protection is a very serious concern for long-term missions on the moon and Mars. Because we have the Artemis project of NASA that intends to send astronauts on the moon in the next few years. But these missions are limited in time. But the idea to send astronauts on Mars, well, it will take about 2-3 years in total as a mission. So it's a very long-term mission. Yes, and it's not so easy to bring back the astronauts to the Earth.
Yes, you've got to bring them back, and you've got to bring them back alive and not sort of dying of cancer.
Correct. We want to send astronauts in a safe condition to Mars, let's say, and bring them back. This is very important.
Now, you can't get as big a magnetic field as we have around the Earth to protect a spaceship on its way to Mars. So how do you work out what sort of shielding would protect the astronauts?
Yes, there are many studies in this field. It's a very hot topic. So traditionally, the vehicles used for spacecrafts are made of aluminum. But actually, in the research that was done in the past 30 years, this research showed that if we add hydrogen-rich material, actually this is a good shielding option. So what is an hydrogen-rich material? So think about the polyethylene that you find in your water plastic bottles that are made of polyethylene. So hydrogen-rich materials have the capability to moderate more the secondary radiation field that comes when you have this cosmic radiation that is incident on the spacecraft and produces a shower of secondary radiation that also is harmful for the astronauts. And research has showed that hydrogen-rich material can be more effective than, for example, aluminum, to shield astronauts. But this is not sufficient. Unfortunately, these so-called passive shielding solutions that consist in adding really shielding materials to your spacecraft are not sufficient. And there is a lot of interest to study magnetic fields that surround the space vehicle that act as a shielding, similar to what our geomagnetic field does with us on the Earth. This technological solution anyway presents technological difficulties, and I know that there is a research in this field, but I think that we will need to wait more time to see any practical application.
As we discussed, we're protected on Earth from a lot of the radiation. So how can you do the research on Earth to protect the astronauts?
Yes. This is a very good point, Ian, because the measurements that we have are very scarce and sparse, okay? So it's very difficult how we do this research on Earth. Well, we do have particle accelerators that are used around the world, but unfortunately, these accelerators can only reproduce partially the cosmic radiation environments because the space radiation environments is made of many different particles with a very wide energy range that can be reproduced with our accelerator facilities. So what we do software simulations where we model in a virtual reality, let's say, the cosmic radiation environments that we would encounter in a human mission to the moon and Mars, and we do theoretical estimations of the doses of radiation that the astronauts would absorb. So we have a synergy between experimental measurements done in facilities on Earth and software simulations. And I'm an expert of these software simulations.
So you can simulate the environment the astronauts will be in and simulate the
Yes.
materials and the method you would use for shielding to get an idea of how much protection you can give them.
Correct. But there is a fundamental problem. There are few problems in this. Definitely, the simulations are a very valid tool and they are used extensively in this kind of problems. But the fact is that we have some sources of uncertainty. First of all, as I mentioned before, the cosmic radiation has a very wide energy range, and we still have sources of uncertainties regarding the radiation interactions with the media. So we have that, and we definitely there are nuclear physics, radiation physics experiments on Earth that try to understand better and to describe better the particle interactions with the matter that are of interest for space radiation of astronauts. But then another crucial point is that there is a source of uncertainty about the biological effect of cosmic radiation. The knowledge that we know about the biological effects of radiation are based on our experience on Earth, on the radiation environments that we have on Earth. But when we go to space, the radiation environment is so different that we are not even certain of which is the biological effect of space radiation in humans. And there is a lot of research in this field in order to understand which is the biological effect.
So when radiation enters a human body, it can go all the way
Yeah.
down to the DNA, can't it?
Absolutely. And you touched a very important point. We study the effect of radiation at DNA level. We look at the strand breaks, at the DNA strand breaks that the incoming radiation does. And that allows us to have a better understanding of the early DNA damage. And this is, again, crucial to understand the biological effect of cosmic radiation in human beings. And with my PhD student, Jay Archer, with a collaboration with Jeremy Brown of Swinburne University, for the first time, we developed a simulation where we predict in a multi-scale approach the early DNA damage in astronauts in different space radiation environments. This will help us to understand better the effect of radiation on astronauts and how to protect them.
So it's just a huge amount of radiation that they're exposed to. So what starts to go wrong when the strands of the DNA are hit by the radiation? What goes wrong?
Yeah. So the cell can mutate, for example, to cancer, or it can die. If it's exposed to a lot of radiation, the cell will die. So these are the effects.
You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com.
Does this mean that astronauts currently are exposed to a lot of radiation, and on a long trip they might expect that it's not just Earth's gravity that they have to adapt to when they get back, but they may need a long course of treatment for radiation sickness?
Yes, this is one of the risks. And I have to say that the International Space Station is a fantastic, let me say, lab where many of these medical problems, let's say, are studied. We have astronauts that spend months on the International Space Station. I have to say that still the International Space Station is at an altitude where astronauts are, again, protected by our magnetic field. So it's in a better condition in and in a better situation. So the ISS, and to study the effect of radiation on the astronauts on the ISS will help us to understand better the issues and problems. Let's think that when we study the effect of radiation on humans, we need a large cohort of exposed personnel. And while there are not so many astronauts on the ISS, so it will take some time to understand more and more the effect of radiation in astronauts. Think that all the missions that we had on the moon consisted of only few days. So we never had astronauts in outer space for months.
And would this much radiation start changing things with the shielding and the vehicles themselves so that they might either get weakened or become radioactive themselves?
Yes, this is a very good question. So when you have an incident, a cosmic radiation on any material of a transfer vehicle, because it has high energy, it will produce a shower of X-rays, neutrons, nuclear fragments, and also these ones can produce harmful effects in the astronauts. So the goal of radiation protection for astronauts is not only to try to stop the incident radiation. That is usually what is done in our environment on Earth, but we have also to moderate and contain this secondary radiation field. And this is a problem that we do not encounter when we do radiation protection on Earth, usually, okay, because the energy beams have a lot lower energy, usually.
And the software you're running for these simulations,
Yes.
do these programs take a lot of computing power and a lot of time, or do you get your answers quickly and you need to ask another question?
No, the simulations take a long time. They are very time consuming. You may ask to my PhD students, but therefore we needed we needed to use supercomputing facilities, and in particular we use the National Computing Infrastructure, which provides supercomputing facilities to all researchers in Australia through merit, through a system of grants based on merit.
And my understanding is that the computing simulations of real-world physics is what's driven a lot of computational advancement, like the graphics cards that now are the fastest consumer computers we can get without a supercomputer, were mainly driven by games people trying to simulate physics, and now physicists use that sort of hardware as well.
Yes, for our simulations, fortunately, the use of GPUs is not so wide, but let me tell you that we are going towards the world of machine learning, artificial intelligence, and there is a large effort internationally to accelerate our calculations with machine learning.
Why do we need to send astronauts back to the moon, where we've already been, and to Mars, where we've already sent robots?
Yes, it's important because it's exploration. So we are human beings, and in our history we are fantastic explorators. And I come from the region of Christopher Columbus, so we are travelers in our region. But an important point that for me is crucial and that motivates also my interest in this research field is that thanks to the study of for example, radiation protection of humans in outer space, this research has impacts in our life on Earth. For example, all these studies in radiation protection and understanding the biological effects of radiation in humans will also help with the cancer treatment on Earth. So it's very important to understand that this kind of research generates an impact in the wider community and in our society.
It's one of those things where following your curiosity seems inevitably always over and over and over to produce information and knowledge and techniques that have a wide application in the world.
Exactly. This is very important. So whenever you think, oh, why we need to spend millions of dollars to look for the dark matter, which is the impact of dark matter in my life? Well, please take the time to look into that research and understand the impact that that research makes in our everyday life, because there will be a technological impact or a knowledge impact that will have repercussions in our everyday life.
Well, it's all interconnected. All of science is interconnected. So one bit of knowledge helps you understand another piece of knowledge, I think.
Yes, absolutely. Think the World Wide Web that was invented at CERN, I mean, in Geneva, Switzerland, in a high energy physics lab. Well, nowadays we all use the World Wide Web. This is a very practical example of the impacts of research in our everyday life.
So, Susanna, how did you get into space radiation physics?
My trajectory started at high school. I was a student in a scientific high school in Italy, and I met a fantastic teacher, and she really got me interested into maths and physics. And then I graduated with a master. In Italy, there is only the master in physics, and then I continued with the PhD. So for the PhD, I was based at CERN in Geneva, in Switzerland, and my PhD was supported by the European Space Agency. And my project was to study and develop simulation tools for radiation protection of astronauts' emissions to Mars in the Aurora ESA project. And that is where my career started. And I found excellent mentorship. So if you are interested in physics and these topics, study these subjects, attend public outreach events. You may try to find a mentor in the field that can support you in your career path. Definitely in Australia, we need more scientists in physics, in radiation physics. There are great career opportunities as a medical physicist in hospital, radiation protection officers, or work in industry in R&D or in education. So there are many career options. So if you are interested in this topic, ask in your school, ask at your local university, or yes, and try to start your career pathway in this field. This area is very multidisciplinary, so you can join this effort as a physicist like me, or like a computer scientist, or like a medical doctor. It's extremely multidisciplinary. And then I suggest to look into local opportunities. We do a lot of research at the University of Wollongong, for example, in space science. We do have high school students that come to have, some not internship, but some research periods with us. Or ask if you are a student at the university, ask to the relevant staff members how you can contribute to research in space. Research in space has become important in Australia, and there is more and more research in space here. This is born by an effort of the Australian government to do more research and to create more industry opportunities in this space. So use this moment if you are interested to become a professional in this field. If you want to do research in space, just try your best to do it. Try to find the opportunities. Don't think that is too hard, or that you need to have some special skill. Just try to network with the right let's say the right people that can enable this type of career, and just do it.
Fantastic. Well, Susanna, thank you so much for your time.
Thank you. I hope it was fine, Ian.
That was Associate Professor Susanna Guatelli from the University of Wollongong, modelling ways of protecting astronauts from radiation on their long trip to Mars and their long stay on the Moon. You can hear Susanna speaking on this subject at the Frontiers of Science Forum at Concord Golf Club in Sydney on Friday the 24th of March. More Frontiers of Science Forum speakers coming soon.
And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please subscribe to the Diffusion Science Radio channel on youtube.com/c/diffusionradio and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including Radio Blue Mountains 89.1 FM in New South Wales, 8CCC in Alice Springs and Tennant Creek, 2MVR in Nambucca Valley, 3MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, and 2XXFM in Canberra. Diffusion is narrowcast on Indigo FM 88 in northeast Victoria. Diffusion is syndicated globally on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 1,000 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Make a donation through paypal.me/IanWolf or join my patrons at patreon.com/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.